This is the third video, the third part of the 9.7 and 9.10 Taylor series and Maclaurin series, Taylor polynomial. Now let's recall. In example 2, we found the Maclaurin series for the cosine x, which is this. Then we kind of use this information to figure out the Maclaurin series for cosine of 2x. All right, so what's the Maclaurin series for cosine 2x? Rather start from scratch, we can do this. Use the functions. Cosine x we know is this, right? And then we're going to figure out cosine 2x. So we replace x with 2x. Got this. Now if we need to put it in the sigma notations, we can do that. So it would be a sum, right? Again, this is even power, so that would be 2x to the 2n over 2n factorial is from 0 to infinity. Okay? Right. In some time, I know sometimes we split this to the 2n and 2n, but I think that's good enough, right? So it will be segmentation. All right. Now let's look at the next example. We find the Maclaurin series for the e to the x functions, okay, the exponential function. Now, if you recall, Maclaurin series means the center 0, so you automatically has these. Okay, so you have 0, no x, or x to the first, x to the second, x to the third, so on. The denominator is always factorial with the same number as exponent, right? 1 factorial is 1. The only thing missing is f of 0, f prime, f double prime, f triple prime, 0 in that order. So all you need to do is, to make it easy, I just write the functions and then derivative in one column. In this case, it's actually easy. The original function is e to the x. Take the first derivative, e to the x, second derivative, third derivative, right? It doesn't change. And then next column is when you plug 0 in. Again, Maclaurin, plug 0 in. Plug 0 in either 0, 1, 1, 1, 1, and 1. So you see that all of these numerators is 1. So you plug in, it's 1, 1, 1, 1, 1. And I'm going to put this to the top, 1 times x squared, 1 times x cubed. And you got a very simple and nice formula, Taylor Maclaurin series for the functions e to the x powers. That one. All right. So again, you see that we have a nice formula we can use to do a lot of things. Now, let me show you again one way we can verify, not verify, but we can use that for some other things that we learned in the past. Let's say derivative, right? So recall, if you're talking about the derivative, and derivative e to the x is what? E to the x. Okay, so this is the one we learned in Cal 1, right? So the question is, why derivative to the x is itself, right? So in Cal 1, we actually go back to the definition. We use some fancy techniques and way to somehow convince you derivative to x is itself, but still it's a very complicated thing to do. If we have the Maclaurin series that knowing e to the x is the same as this series, then things much easier. Way much easier. Why? Because if I want to take the derivative of e to the x, right? I don't know the answers. I do, but I'm going to check it later. Why don't we take the derivative of the right hand side because they're the same, isn't it? That's the same. I'm not going to rewrite the whole thing, just it takes time, right? So we're going to take a derivative of the right hand side. Okay, so what's the derivative of 1? 0. What's the derivative of x? It's 1. Derivative of x squared over 2 factorial. That's 2 times x, bring the 2 down. 2 and 2 cancel. 2 factorial is 2, so we got x. Derivative this one, bring the 3 down. 3x squared over 3 factorial. And then that will be 4x cubed over 4 factorial. Now don't forget that factorial, 3 factorial means 3, 2, 1. 3 times 2 times 1. Right, if you cancel the 3, then you have 2 times 1 left, or 2 factorial. This is 4 times 3 times 2 times 1. If you cancel the 4, and then you're left with what? 3 times 2 times 1, or 3 factorial. So after you can simplify, you see you're left with here's is a 1, here's an x, next one here is x squared over 2 factorial, next one here is x cubed over 3 factorial, and the next one you can see will be x to the 4 over 4 factorial, right? And let's continue. Let's continue. And what you see as you go and continue, you see that one's the same as the original, right? So that's the same as e to the x. Okay, so that is the same if you take the derivative on the right side. Likewise, if you want, you can take the integration. So when you integrate both sides, it's going to be the same anyway. Okay, so that's an interesting thing that you can do, or you can check. Right. So again, you can check other things like what is e to the 0 power? Like 0 in, all gone except 1. Right. Or we can do other things. You know, again, if I'm gonna make things complicated, say what's e to the root 2? You see this one, even, I mean, if we're gonna have to do this in calculator, we can, but it's hard to explain even in calculator or computer how to raise e to the root 2 means. If you have e to the third powers, I can say, oh, that's easy. That's just saying, okay, let's take e times itself 3 times. But then e raised to root 2, what is this, right? So now when you have this equivalent series, then I can say, well, if you want to do e to the root 2, you just take 1 plus root 2 plus root 2 square over 2 factorial, etc. So the right hand side is much more easy to explain, to implement, right, rather than the e exponential function itself. Okay. Let's look at the next example. Now the next example is the sine of x, by the Maclaurin series, sine of x. Again, we're going to do the same thing. It's very mechanical. You start with the function sine, right? You take the first derivative, cosine, second derivative, negative sine, and negative cosine, and back to sine, right? It's like cosine. Keep taking derivative. This column right here, you're going to plug in. Again, Maclaurin series means center at 0. Plug 0 in, I got 0, cosine 0, 1, sine of 0, 0, cosine of 0 is 1 with a negative. That's negative 1, and back to 0. And then you plug in the formula. Okay, again, the formula is always the same for Maclaurin series. With these coefficient numerators here, we plug in. But this time when you plug in, you see every other term dropped out, and actually all the even terms got dropped out. even power. So you see that we left with x cubed 3 factorial, next one x to the 5th over 5 factorial. So this is really an alternate series with the odd powers only. Odd powers only, okay? Now, what's interesting about this thing is, if you recall, the sine function is what do we call? What type of function is it? It's an odd function. Remember even odd? So an odd function is a function actually symmetric with respect, this is the cosine, with respect to the origin, right? In other words, the odd function satisfy what we call f of negative x equal negative f of x by definitions. And one thing is what we can see clearly is the odd function is, you see all the powers are odd. All the powers are odd. Okay, if you plug in negative x, you'll be negative, negative, negative. So we use essentially plug the negative, everything turned to negative, so all the side flip. So end up with the new functions. It just the opposites of the original function. You can actually check. So that is an odd function. When you graph it, of course, this is, you know, the graph of the sine look like. It's going to go like this, and it's actually symmetric respect to the origin. If we backtrack to the cosine x example, you can see we talked about even odd. It's actually an even function, isn't it? See this one? Actually, we have done of these. So that is an even function there. See the powers is even. And if you plug in negative x, it's gonna be, it doesn't change anything, right? It's gonna be the same as original. So that's why we do have, if you recall, we do have these trig identities from trig class is what's the cosine of negative theta. It's the same as cosine of theta, right? Cosine of negative pi half is the same as cosine of pi half because it's even. Plug in, that's what you got. And same thing for the odd function here in example 5. For the psi function. For the psi function, we have these identity that is sine of negative theta. It's the same as negative sine theta. Again, you can check that.